Today we are going to start another topic, that is semaphore. Now, in previous lectures of process synchronization, we had picked that what is critical section, what are necessary conditions to solve critical section, that was mutual exclusion, progress, bounded waiting. Then we moved that how to deploy such kind of solution which can incorporate all these conditions, and we have picked various solutions of it. Further, we moved into hardware-based solution. We had picked that we can disable all the interrupts, or we can move for the TSL, that is set, test and set lock. Now, today we are going to pick another solution, that is by deploying the semaphore. Now the thing is that what is semaphore? Semaphore is simple a variable, nothing else. The only thing is that usage of this variable. This variable is used in such a way that it can provide effectively the solution to the problem of mutual exclusion specifically, and a solution to the problem of organizing our resources in effective manner, so that no two or more processes can pick one resource at any instance of time. So that is the fundamental of semaphore. So let's try to pick that there are two kinds of semaphore, or there are two kinds of usage of semaphore. One is known as binary semaphore and the other one is counting semaphore. Now binary semaphore is just like your variable turn, as we had picked earlier, that what I'll do, I'll make value of turn, it will be either 0 or 1, or it will be either true or false. So whenever any process wants to enter, it needs to make it true, and then if it is true, then nobody can enter into the critical section until and unless that process has released that semaphore or that particular turn. And that is the main reason that it is also called mutex. Mutex means mutual, that is mute, and X means exclusion. So mutual exclusion in shorter term is known as mutex. So binary semaphore is also known as mutex because it provides the mutual exclusion. So that was the thing which we had already discussed. So we are not going to focus this thing again. Now today we will discuss about counting semaphore. Now why or how this counting semaphore is different from other solutions. So let's pick that till now whatever solution we had discussed, that is for n processes. Here we are focusing on that there is one critical section, and if several processes wants to enter into that critical section, then how to manage it. That is we have done so far. Now suppose what I have suppose three critical sections or three resources. Let's pick that I have three printers and I have five processes. Now, how to assign these three printers to these five processes? We have not done any solution related to these kind of situations where I can have n resources or n critical sections. So that thing is handled by counting semaphore. So how counting semaphore handle it? Because we have already said that counting semaphore or semaphore is a simple variable. So the thing is the usage of that variable, that how to use that variable in such a manner that it can provide solution to such complex problems. So let's try to pick. For deploying counting semaphore, we are going to use two functions. One is wait and the other one is signal. Now, wait will be my entry section. Then there is critical section definitely, and at exit section, I have signal. So if I want to share any kind of resource, so what I am having? I am having one wait and one signal. If somebody wants to acquire certain resource, then it has to check the wait system, and if it got permission, it will execute or it will pick that resource, and after releasing it, it will signal or process will signal that I have released that resource and anybody can use it. So in this manner I can solve it. Now let's take one example that closest to this implementation of semaphore, that is that suppose I moved into cyber cafe where there are 10 systems currently available. Now, there are one simple system is that whenever anybody wants to pick that particular system, he or she will enter. Most of the time, the person who is in charge of that cyber cafe that will enter your name and detail and allot one system to you. And what it will do, that after allotting the system, it had 10 systems, so it will do that now there are 9 remaining. Now in this way it will move and decrement the value in such a manner that if it got 0, then it means that no system left, and hence after that if somebody arrives and wants that please give me that system, it will say that I cannot give, please wait. And that is the overall thing, that further if somebody has released the system, what it will do, it will add by incrementing the value. So from 0 it will become 1, and then if somebody asks that I require certain system, it will give that system. So that is one simple process. So Semaphore use the same real-time concept for deployment and management of multiple resources. So what we had picked that there are two functions, wait and signal. Now here is the code of wait. Wait says wait as a semaphore. While value of semaphore is less than or equal to 0, it means that I do not have any resource left. Then what it will do? No operation. I am not going to perform anything, and process or person will continually move and wait for its chance. Otherwise, please make sure this is the semicolon here. Otherwise, if this condition is not true, then S minus minus. So earlier, if I had suppose two resources, then S minus minus says that pick one resource, give to some person, and make value of semaphore is 1. The value of semaphore S tells it that how many resources left. Once again, be sure that value of semaphore tells that how many resources are left. So since it got 1, so one resource is left. Now in this way system will move further, and what it will do, that suppose next process arrived, so it will again check that value of s, is this value is less than or equal to 0. If value is 1, then definitely this condition get false and this will become 0. Now there were two processes, both got chance for resource. Now if third process arrived, process 3, so what it will happen, that while s is less than equal to 0, now value of semaphore is 0. If value of semaphore is 0, then no operation. Now third process will move here continuously until and unless any process will release itself. So suppose P1 had released that particular resource and incremented that S. and s once got incremented, so it becomes from 0 to 1. Once it got 1, this loop will tell that now value of s is 1. So now I can provide to the third process and it will again make it 0 and occupy it. In this manner, the system will move on continuously. So that is the semaphore and implementation of semaphore. Now, there are two major questions. The first question is that why we are having s value here is s is less than equal to 0. It should be s is equal to 0. Now, reason is uh, of question is that since I will never move into negative value, then why I do not have s is equal to 0? Why I am having this less than sign? So what is your possible answer for it? It is absolutely right that yes, s is less than equal to 0. Instead of that, I can write s is equal to 0. So what is reason behind it? Please once explore the reason behind it, and in our discussion class, definitely if you will ask, we will discuss that thing, that why we have less than sign here, and that we will discuss in our discussion class. So I had given you the question here, that why it is having this thing. Solution will be discussed in discussion class. Now the next thing is that okay, we got one specific thing. Why I am having continuous infinite loop? Don't you think that this loop will waste my CPU cycles? That each and every time it is continuously checking for availability of the system. In other way, which we had taken one example of cyber cafe, let's take the same situation that after allotting all the available systems, now suppose one person arrived and you was in charge of that cyber cafe, and he asked that is the system is available, and you told that no, it's not yet available. Whenever it will get available, I'll let you know. Now, there are two ways to handle this situation. The first one is that that particular person will ask continuously to you that is the system is available, is the system is available, is the system is available, and that is what this particular loop is doing. And second and most effective solution is that what you will do, you will say that sir, please do not ask me continuously, wait for a while. Whenever any system will get available, what I'll do, I'll let you know. So what you are going to do, you are going to make one waiting zone where you will say that sir, please sit here, I have noted down your number, and once anything get free, I am going to call you and I am going to tell you that yes, now it is available and please move further. So I think the best solution is the second one, and that is here that we need to break that spin lock, that is known as spin lock. Continuously asking, that is spin lock. Spin lock. Please be careful. Spin lock is not any kind of locking mechanism. It only says that process is waiting continuously. It's pinging continuously. So that is known as spin lock. So how to break that spin lock? So solution to break spin lock is just once again with respect to the real system, which says that what we can do, we can take one waiting zone where I'll put all the processes or all the persons who are coming after after completion of my availability, then what I'll do, I'll tell each and everyone that please wait, and one by one I'll pick according to that waiting list. So that is the solution. So let's check this implementation of that particular solution. Now here I am going to utilize two things. One is known as block and another one is known as wake up. Block will be used that suppose if value of semaphore is less than 0 or if resource is not available, then what I am going to do? I am going to block that process. Here block means that process will wait. And wake up says that whenever I got any new resource which was released, then I am going to wake up one process from that waiting zone or from that blocked zone and bring that process and give that resource to that particular process. So let's see the implementation of that thing. Now here in wait section, what I have done, without checking, first of all, I am going to decrement the value. So suppose I have at the start 3 resources. So let's check one by one. Process P1 arrived. So value becomes 3 minus 1, that is 2. And it move into the next one. If s dot value, we had earlier used here one structure to define that semaphore s. Here I have used the short form s. So which says value and one list. So let's pick here that if s dot value is less than 0, why less than 0? Why not less than equal to 0? Because at the start I am going to make minus. So if suppose value of s is 1, so I'll provide that process, and because of that decrement it will become 0. So if I'll have less than or equal to 0, instead of giving that one resource to particular process, it will move into the list. Hence I have less than 0. So if s is less than 0 means I do not have any resource left, add this process into the list. So earlier for P1, yes, I have. For P2, that becomes 2 minus 1, 1. I have given that process. For P3, 1 minus 1, 0. That was the case which we had discussed. Definitely P3 also got chance. But for P4, once P4 arrived, P4 has done s dot value minus minus. So 0 minus 1, it becomes minus 1. Since value is minus 1, what it will do? It will add into the list. So here got P4. P4 is in waiting zone and P4 got blocked. So instead of continuous checking, which was earlier in spin lock, now I am blocking that process, that now you cannot ask me continuously. I am going to reply you once I'll have the resource. Similarly for P5, I got minus 2. Now here, as you can see, positive value of semaphore is reflecting number of resources. Negative value of semaphore is reflecting number of processes in waiting. So be careful. Positive reflect totally different thing. Negative reflect purely different thing. Positive value of semaphore here represent number of resources available. Negative value represent number of processes are in waiting queue. So here we had P4 and P5. Why? Because minus 2 tells that two processes are in waiting zone. Now suppose after certain time, one process has released its resource. So s dot value got plus plus. Once that process has released, irrespective anyone, suppose P2 has released it. So once P2 has released, the actual value of semaphore was minus 2, so it becomes minus 1. And s dot value says that if the value of semaphore is still less than equal to 0, it means there are certain processes which are in waiting zone. So what I'm going to do, I'm going to pick process from my list by making certain ordering or certain sorting. And suppose I have picked the P4 and I'll give that resource to the P4. When I'm going to give resource to the P4, when value is still negative. Now at next time, suppose P3 has released its resource, so I got that value is minus 1 to 0. And I hope now you got that why I am having less than equal to 0, because minus 1 to 0, it says that yes, there was one process that was P5 which was waiting, so pick that process. Now since I have value 0, it means that no process is waiting in queue. So suppose another process, suppose P1 has released its resource, so it will be straight away added to the semaphore without giving anything to any process, because no process is arrived yet. So that is overall working of s dot value and semaphore. I hope you got that why it is less than equal to and why it is only less than. So that is how it works without continuously using the spin lock. The same concept was implemented by using block and wake up. Wake up says that after picking that value, wake up that value or pick that value from list and provide the resource, that is for wake up. So that is overall counting semaphore. Uh, so we had picked uh, complete aspect of semaphore, that is binary semaphore, counting semaphore. Then in counting semaphore, both ways, one is with spin lock, one is without a spin lock. We had uh, discussed each and everything in detail. So that is all for semaphore and process synchronization.